What happens when your FastMCP tool encounters an error during execution? Should the client just crash or get a clear indication of what went wrong? We'll implement a test case that deliberately triggers an error condition, then verify that the error propagates correctly to the client. You'll see how FastMCP handles exceptions in tool execution while keeping the connection stable.
Async def test tool execution with error. Test that tool errors are properly handled. MCP, FastMCP, test server. At MCP, tool. Def divide a int b, int float. If b equals 0. Raise value error, cannot divide by 0. Return a /b. Async with client, MCP as client. With pytest, raises exception. Await client call tool divide, a 10b, 0.
This demonstrates error handling in RPC tool execution through declarative testing. The test verifies that exceptions raised within decorated tool functions propagate correctly to clients, maintaining a clean separation between business logic and error handling. What makes this distinctive is how it validates the entire error flow from tool implementation through transport to client reception. The pattern works by treating tool errors as first-class concerns rather than edge cases. By explicitly testing exception propagation, you ensure the framework preserves error context across process boundaries, while the decorator approach keeps error handling logic out of your core implementation. This creates a robust contract where tools can fail naturally without requiring special error wrapping code. This approach matters because it enforces reliability in distributed systems where errors often get lost or obscured. By testing the full error propagation path, you catch transport-level issues that might silently swallow exceptions. The trade-off is slightly more test code, but the benefit is bulletproof error handling that works consistently across all transports and client types. Let's break it down line by line.
Async def test tool execution with error.
This defines an async test function to verify error handling in tool execution. It ensures the MCP server properly surfaces and propagates tool errors to clients, preventing silent failures. The async prefix enables testing of asynchronous tool calls.
Test that tool errors are properly handled.
This docstring declares the test's purpose, verifying that tool execution errors propagate correctly to the caller. It ensures the system handles exceptions gracefully rather than silently failing, which is critical for debugging and reliability.
MCP, FastMCP, test server.
Instantiates a FastMCP server instance named test server. This creates the core execution environment for testing AI callable tools, handling tool registration and request routing.
At MCP, tool. Def divide a int b, int float.
The @MCP tool decorator registers this function as an AI callable tool. FastMCP converts the type hints and docstring into an executable schema, enabling the AI to validate inputs and understand the tool's purpose before invocation. This pattern standardizes tool definitions across the system.
If b equals 0.
This is a validation check that prevents division by 0 errors. It enforces the mathematical rule that division by 0 is undefined, ensuring the tool fails fast with a clear error rather than propagating invalid results.
Raise value error, cannot divide by 0.
This explicitly raises a value error when division by 0 is attempted, enforcing input validation. It transforms a silent runtime crash into a controlled, testable error path, critical for reliable tool execution in production systems.
Return a /b.
This performs the actual division operation when valid inputs are provided. It's the success path that executes only after the error check passes, demonstrating the expected behavior when no exceptions occur.
Async with client, MCP as client.
Context Manager pattern with async support. The async with establishes a temporary client connection to the FastMCP server, guaranteeing proper resource cleanup when the test block exits, even if the test fails. This prevents connection leaks between test cases.
With pytest, raises exception.
This is pytest's exception assertion pattern. It verifies that the expected value error is raised when dividing by 0, confirming proper error handling in the tool execution flow. Without this, silent failures could mask critical validation errors.
Await client call tool divide, a 10B, 0.
This triggers the tool execution with invalid input, forcing the division by 0 error. The test verifies that FastMCP properly surfaces tool exceptions to the client rather than suppressing them. This ensures error transparency in AI tool integration. Error handling pattern. FastMCP's error handling transforms Python exceptions into structured MCP protocol errors, ensuring AI clients receive consistent failure information regardless of implementation language. The raise on error equals false parameter lets you inspect raw error responses without exception handling, but requires manual status checking. This pattern creates reliable AI interactions by making failures as predictable as successes.
The error that speaks every language is the one that needs no translation.